everyone. In the previous class we discussed about some of the basics pertaining to rock engineering, and we discussed about unconfined compressive strength tests. I told you that how we can conduct the test, how we can find out the UCS, and how we can find out the modulus of the intact rock using the results of UCS. So, today we will continue this series of the discussion on basics of rock engineering, and we will discuss about the tensile strength and shear strength of intact rock. So, to start with, we will first focus on the tensile strength of rocks. Basically, these tensile strength of rocks can be obtained by two types of methods. One is the direct method and the second is the indirect method. In direct methods, the specimens are made in such a manner that ends of the specimens, they are held together and then they are subjected to the tensile forces. The failure takes place in that mode only, and whatever is the strength that we obtain, that directly gives us the tensile strength of rocks. But the problem with direct methods is that you need to make special specimen of some special type of shapes, which may not be that easy to make, because of the reason that if you have to grip the specimen and subject it to the tensile force, then when you are gripping the specimen there, the shape of the specimen should be very typical, so that there are no stress concentration and the specimen will fail under tensile stresses only. So, such things do not make direct methods very helpful as far as determination of tensile strength of rocks are concerned. So, there comes the indirect methods in which we apply the compressive force to the specimen, but then we obtain the tensile strength. So, one such test is the Brazilian test, which originated from South America, and this is the most commonly adopted test to obtain tensile strength of intact rocks. So, that is what that we are going to discuss now. So, as I mentioned that this Brazilian test, it originated from South America. In this you have a circular solid disc which is compressed to failure across the diameter. So, that means that you have a circular solid disc which you will subject to the compressive loads rather than the tensile load. The material in this case is assumed to be homogeneous, isotropic and linearly elastic. There are some limitations with respect to this test, which is mentioned here, that this test is only valid when primary fracture starts from the center spreading along the loading diameter. So, the stress distribution along that diameter becomes of the greatest interest. Take a look here. This is a picture which shows the apparatus for the conduct of Brazilian tests. You can see that there is a grip here, two blocks are there. So, the specimen is held between these two grip, and then with the help of this lever, you have a jack here. With the help of this, you apply the compressive load to this assembly, which can be measured in this gauge, pressure gauge, and that directly gives you the tensile strength of the rock. So, we have the expression, and there you just have to make some simple substitution and you will be able to obtain the tensile strength. Now, before I take you to those expression, first let us understand that what are the various requirement of the test. So, preferably we go for NX size specimen with length to diameter ratio to be equal to 1. That is, the minimum slenderness ratio that we take is 1. Then the tensile strength increases with increasing rate of loading above 0.1 ton per minute, and it reduces with the increase of the water content. So, in case if the sample is saturated, obviously its tensile strength is going to be less as compared to the dry sample of the same rock. So, as I mentioned, this picture clearly shows how the loading will be applied. So, along this diameter, the loading is applied, and see, it is compressive in nature, and it is assumed that the crack will start from this center and it propagates towards the circumference or towards the end of this disc. So, the tensile strength is found to be greatly influenced by the loading along the plane of weakness or across it, in case you have the anisotropic specimen of rocks such as slate, schist or phyllites. Now, if you increase the volume or the length of the specimen, the tensile strength reduces. Why so? Because when you have larger volume of the specimen, there are going to be more number of microfractures or microcracks present in that specimen, and that will result in the reduction of the tensile strength of the intact rock. So, I mentioned to you that we need to use an expression to determine the tensile strength of the rock. So, this is the load F at which there is going to be the failure of this specimen. So, that load divided by pi r naught into T, that will directly give you the tensile strength of the intact rock, where this r naught be the radius of the solid disc and T be its thickness, that is the dimension in the plane perpendicular to the plane of the screen. So, why there is this negative sign? Because we are representing compressive strength as positive and tensile strength as negative. That is why we have kept a negative sign here while representing the expression for tensile strength. This tensile strength is represented by sigma T. So, here is the picture where the sample is subjected to Brazilian test. So, you can take a look that how the specimen is held between these two grips. This is the broader look and this is the closer look of the specimen, and you can see that how the cracks are developed along this diameter. Now, in the absence of any measurement, that is, let us say we are not able to conduct the Brazilian test or any test for that matter to determine the tensile strength of rocks, then this tensile strength is assumed as some fraction of UCS, that is unconfined compressive strength, which is represented by sigma c. So, usually this tensile strength is taken to be 1/10 of the UCS value. So, this more or less gives you the good estimate of tensile strength. So, some typical values of the ratio of compressive strength to tensile strength has been given in this particular table. So, here you have this coarse grain Nevada granodiorite, For that, this sigma c by sigma t works out to be 12.1. In case of the somewhat weathered quartz monzonite, you have 15.9, and for a particular type of basalt it worked out to be 11.3, and for Nevada tuff it is exactly 10. So, basically to the tune of 10 to 15, you will get a very good estimate of the ratio of UCS to the tensile strength of rock. Now, coming to the shear tests, so there are basically two types of shear tests, or I should say two categories of shear test. In one type of test where the shear strength is determined without the specimen being subjected to the compression. So, only the shear force is applied without the application of any compressive force on that shear plane. Second category belongs to the methods for determination of shear strength with compression. Right now, we are going to discuss this second category because these are the most commonly adopted shear tests to obtain the shear strength parameters of intact rocks. So, the first test here is the triaxial shear test, in which we prepare the rock specimen as per ISRM specifications. This we discussed in earlier class. And NX size is preferred. So, when I say NX size, this means it is 54 mm diameter. Then the confining pressure is applied and is maintained through the oil which is filled in the triaxial cell. Now, if you compare this triaxial shear test for rocks to that of the soil, in case of the soil, this confining pressure is applied and maintained through the water. See, the shear strength of the rock is much larger as compared to that of the soil, and water will not be able to apply that much of the confining pressure which is needed in case of the rock samples. That is the reason that we apply this confining pressure through the oil that is filled in the cell rather than water. Coming to the axial load, this is applied at a constant rate of deformation or loading in a loading machine. So, when you have the constant rate of deformation, you will have a particular, let us say, few per minute. And if you have the loading, then you have particular load per unit time. So, in this case, at least 3 specimens should be tested under different confining pressure. So, minimum of 3 specimen, but if you recall, we had the discussion in the previous class that when the rock is having more heterogeneity, then in that case we should have at least 3 specimen for each confining pressure, and minimum 3 confining pressures are needed. So, that ideally one should have total of 9 tests to complete one triaxial test. However, in case if you do not have that many sample, then at least 3 specimen each at different confining pressure should be tested to complete one triaxial shear test and to obtain the shear strength parameters of the rock. Now, this is the picture of the triaxial shear test machine that we have in our lab. So, this portion you can see here, the sample is mounted, and this is a servo control machine, and the control is there. It is, although it is not visible here, but then a system is kept in this enclosure where when you apply the load, it gives you the idea that okay, corresponding to this load, this is what is the deformation that is taking place, or corresponding to this much of the deformation, this much is the stress that is being generated. So, ultimately what we get after the conduct of triaxial shear test, we get stress strain curve. So, these are plotted with deviator stress, that is sigma 1 prime minus sigma 3 prime and the axial strain. So, you can see in this particular figure that on y axis we have this sigma 1 minus sigma 3 prime, and on x axis we have this epsilon 1, which is representing the axial strain. Modulus and the failure deviator stress for each confining pressure is essential. Now, if the strain gauges, they are attached to measure the lateral strains also, we can also estimate the Poisson's ratio from the triaxial shear test. Now, here you will observe a very interesting phenomena that is happening. As we increase the value of sigma 3, you see how the shape of stress strain curve changes when for the lower value of sigma 3. So, here in this direction it is increasing, which is shown here in this figure. So, here let us say this is sigma 3 1, say this is sigma 3 2, this is sigma 3 3 and so on. So, basically this sigma 3 1 is smaller than sigma 3 2, that is smaller than sigma C 3. So, what happens when you conduct the test at low confining pressure, you get the brittle kind of behavior as far as the stress strain relationship is concerned. You see, it goes to the peak, and then the drop here in the stress is very sharp as compared to when you have increased the value of sigma 3. That is, you take a look here corresponding to this particular plot, and here it is, there is no drop. So, practically it has become like elastic, perfectly plastic kind of behavior. So, basically as we increase the value of sigma 3, there is a transition in the material, that is, it is transitioning from the brittle to the ductile behavior. So, it is the same rock, but the value of confining pressure is making it behave as ductile or maybe brittle at low confining pressures. Now, as far as the stress strain relationship was concerned, that we saw, but then how to determine the shear strength parameters. So, for that you can develop the failure envelope using the more stress circles, because you know what is the shear strength and the principal stresses. So, you can have here, that is, this is tau and then sigma. So, you can have this kind of more circles, and then maybe you can draw the common envelope to it, and you can determine here it is, this is going to be maybe C and this is phi. Now, here we are making an assumption that this material is following the Mohr Coulomb failure criterion, which may not be true. So, we will learn in brief that what all are the various failure criterion which are available for rocks and rock masses. But let us say I assume that it is following Mohr Coulomb failure criterion, then using this Mohr stress circles, we can determine the value of C and phi. Now, similar thing can be determined using stress path method. How? In case of the Mohr circle, the state of stress is represented by a circle, while in case of the stress path method, the state of stress is represented by a point. So, here what you need to do is you will plot P Q curve. So, here it is Q and here you have P. Every state of stress will be represented by a point, and then what you do is you try to fit a straight line to this, and there is the ordinate, say here it is A, and there is this slope delta. Now, if you just try to compare the equation of Mohr Coulomb failure envelope here and the equation here, you will establish a relationship between C, phi, A and delta. So, either you can represent your test result in this form, or using the stress path method or PQ plot, you can determine this and find out the C and phi, which are the shear strength parameters for the rock. Now, as I mentioned that you can find out the shear strength parameters. Now, the assumption that is involved here is that the failure envelope is linear within the range of confining pressure that you adopt. But this may not always hold good, and the result therefore will be a non-linear envelope. Okay. So, you see that as I mentioned that if you have here as tau and this as sigma. So, in the beginning you may have this kind of envelope which is not linear but non-linear. Okay. So, assumption that we are involving in case of the triaxial shear test, that is the failure envelope is linear in this case. So, you can go ahead with the non-linear one also, but then there are other failure criterion which are kind of modified Mohr Coulomb failure criterion, which you must adopt to represent the failure criteria that the material is going to follow. So, we learnt about the determination of the tensile strength of the intact rock using an indirect method, that is Brazilian test, and then we also learnt about the determination of the shear strength parameters using triaxial test. So, we will continue this discussion in the next class. We will touch upon some of the other basics related to rock engineering. Thank you so much.